Hello, AP Stat students. Today we will be starting Unit 8 and we will be doing Chapter 11 notes. It is called chi-square test for categorical data. Why do we have another type of significance test for categorical data? We've already done our significance test, our z-significance test. Well, a one-sample z-test only analyzes the proportion for one category. A two-sample z-significance test only analyzes the difference in proportions for one category. What if we want to analyze the proportions for all categories? So we have a test for that, and that is called a chi-squared test for categorical data. And the one that we're going to talk about today is the first one. It's called the chi-squared goodness of fit test. This test takes one variable and for example, maybe like favorite color. So one categorical variable and analyzes its distribution. And so we might be looking at blues and greens and reds instead of just, if we did a z-test where we had one category, we'd be just looking at one color. Among all of the categories, it compares the expected distribution to the actual sample distribution. To determine if there is a difference in the distributions. For this test, we compare counts, not proportions. And we've not done that before. We've always looked at proportions. Now we're going to look at actual numbers. So we're going to look at counts. The next two we're going to talk about later in the chapter, and that's the chi-square test for homogeneity and the chi-square test for association and independence. These are the exact same test, but they differ in how the data was obtained. So the chi-square test for homogeneity, we continue analyzing distributions, but now we are checking if the distribution is the same or different. And here we will be looking at two samples for several populations or treatments. For the chi-square test for association independence, we sample or experiment from a single population and break them up among multiple variables. We then check to see if there is an association between those variables. Okay, so what does a chi-square distribution look like? This distribution is a measure of the distance of the observed count, so what you actually see in your samples, sample data, from the expected count. Unlike a normal distribution or a t-distribution, the chi-square distribution is not symmetrical. And we know that a t-distribution was just flatter. The chi-square distribution does change based on the number of categories, creating a degrees of freedom. And before, when we had the t-distributions, we did the sample size -1. It's different when we were doing a chi-square distribution. And I'll tell you here in a second. Okay, so if you look at the purple, red, and blue distributions, the purple one looks more of like an exponential decay, and then the red one and the blue one both are skewed, and they're both, as you can see on all three of them, they're right skewed. So the chi-square distribution is right skewed. And there's a lot of bunching up at the very front. And the reason why is because if you notice here, you only see positive values. So it's a distribution with only positive values. As the degrees of freedom become larger, it becomes less skewed. As the degrees of freedom become larger, larger values become more probable, meaning there will be a greater p-value. The mode will be, which is the peak, will be at whatever the degrees of freedom is, minus 2. The mean will be the same as the degrees of freedom. And the variance is, remember, standard deviation squared, will be 2 times the degrees of freedom. Here's the main thing. How do you get the chi-squared statistic? And this is on your formula sheet. So you don't have to memorize it, but the more you use it, you won't have to even look at it. First of all, let me just tell you what the Greek letter chi, it's a diagonal line like that and like a fancy looking X. So that's chi. So chi squared is equal to the summation and of the observed minus expected squared, so you don't have any negative values, divide by the expected. So that's on your formula sheet, and that's what we'll be using to get this chi-squared statistic. And when we get the chi-squared statistic, we wouldn't be doing a normal CDF or a TCDF. We would be doing a chi-squared CDF. So the conditions for any chi-squared test, there are 3, and the first one is random. So simple random samples to infer to the population, or random assignment assigned for randomized treatment experiments. Instead of the normal, because you're not going to get a normal distribution, you are going to look at what is known as large sample. So all expected values are greater than or equal to 5, and all of the expected counts must be listed. It is okay if expected counts are decimals. For the independent condition, individual observations are independent. That's the same. Population is at least 10 times larger than the sample size. So when we've done all of these conditions for either proportions or means, we've always used the random and independent condition, and they've differed in that normal condition. But now this is not even using the normal condition. Okay, now for the 4-step process for the chi-squared goodness of fit test, we have a state proportion, and generally, you're supposed to do the state part before you even collect data. And here we're just going to analyze data in this class. Okay, so we want to perform a chi-squared goodness of fit test at the whatever significance level, 0.05. You do list a null and alternative hypothesis. It's not written like it was written before using proportions or means. So what are the expected proportions based on the population? That would be in your null hypothesis. And for your alternative hypothesis, at least one of the PIs is incorrect. And you would explain what the PI would be. So where P, whatever that category is equal to the true proportion of whatever. And we'll do an example. Then you check if conditions are met. Oh, in the plan section, you would say that you are doing, right here, perform a chi-squared goodness of fit. And you can abbreviate that because oftentimes that is what you will see. And then check for the random, large sample, independence condition. Then here's your formula again. So the chi-squared is equal to the summation of observed minus expected divided by the expected. And you have to list out at least 2 of the terms. So, and the rest can be done by calculator. So when I say list them out, you're going to have something over something plus another something over something plus ... and you calculate the p-value. So you're going to do a chi-squared CDF with lower bound, upper bound, and the degrees of freedom, which now here, it's not going to be the sample size minus 1. It's going to be the number of categories minus 1. And remember, the p-value is the probability value. It's a probability of getting the chi-squared statistic if the null hypothesis is true. We then compare the p-value to the significance level. If the p-value is less than the significance level, we reject the null hypothesis. If the p-value is not less than alpha, we fail to reject. And then always interpret those results in context. We reject the null, so we have convincing evidence of the alternative hypothesis. But remember, tell what that is. Don't just say we have convincing evidence of HA. Just make sure you tell in context what it is. We fail to reject the null, so we do not have convincing evidence of the alternative hypothesis. Okay, we will do one example. According to the 2000 census, of all U.S. residents aged 20 and older, 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, 15.5% are in their 50s, 22.8% are 60 and older. The table, so these values that I underline are your expected values. The table below shows the age distribution for a sample of U.S. residents aged 20 and older. So from the sample, these would be the observed values. Members of the sample were chosen by randomly dialing landline telephone numbers. Do these data provide convincing evidence that the age distribution of people who answer landline telephone surveys is not the same as the age distribution of all U.S. residents? So most of the stuff is written out for you, so you just have to fill in the blanks, so you don't have to write that much. So under the state, we will perform a chi-squared goodness of fit test at the 0.05 significance level. And then so our null hypothesis, we're going to list the expected proportions. So for the 20 age group, it's 19.1%, so write it as a decimal. For the 30s, it's 0.215. For the 40s, 0.211. 50s, 0.228. Or I'm sorry, 0.155. And then for the 60s, 0.228. Okay, so those are, you list all of them in your null hypothesis. For your alternative hypothesis, at least one of those is incorrect. So at least one of the PIs is incorrect. Where, here we're defining PI is the true proportion of people in their 20s, 30s, 40s, 50s, and 60 age groups. Okay, now check conditions and perform. We need to always state what test we're using. So perform a chi-squared goodness of fit test. Okay, so for our random condition, it is a simple random sample of 1,048. So here's your total. U.S. residents. +20 years old. Okay, for our large sample, so this will take a while, but you have to list every single one. So to get each of these values, you take your expected proportion. So for the age 20 group, you would take 0.191 and then multiply it by your sample size, and that's the expected amount that's what you expect to get. So 0.191 times 1048 will give us 200.17, which is greater than or equal to 5. And remember, it's okay to get decimals. For the next group, so 30s would be 0.215 times 1048, and that gives me 225.32. So always list what values you're getting before you just say, hey, well, I know that's going to be greater than or equal to 5. We actually need those numbers, so you have to do the calculations anyway. Next one, 0.211 times 1048. That is 221.13. It's greater than or equal to 5. Okay, for your 40s, for your 50s, 0.155 times 1048. That is 162.44, greater than or equal to 5. And last group, 60s, 0.228 times 1048 is equal to 238.94, greater than or equal to 5. So all of them were fine. And for the independent condition, it's reasonable to assume that there are more than 10,480 people in the U.S. 20 plus years. Here we go. Okay, so for in our deuce portion, so our calculation portion, what do we write out? So we are going to find our chi-squared statistic. So chi-squared is equal to, okay, and we said we would write out two of them. So the observed value, so for the first one, it'd be 141. So these are your observed. That's what you get from your sample. So 141 minus the expected. So from the 20s group, that was 200.17 squared, and then divided by the expected. List one more. So I'm going to do it for the 30s age group. So we have 186 as our observed minus our expected was 225.32 squared over 225.32. And of course, we're not going to write all these out. That would be too many. I mean, sometimes you have like 15 of them. So plus ... and we are going to get an answer. We're going to do the rest of this in our calculator, and I am going to show you that video, and then we can fill in our conclusion. So I will do the rest of this problem in the video on the graphing calculator. So have a great day, algebra or AP Stat students.